Now difference between the cis and trans isomers, the cis is unsymmetrical, trans is symmetrical. I said you, this is line of symmetry. Now due to which trans is more stable than that of the cis. As it is symmetrical, so its stability is more. See, any object is symmetrical, it is more stable. It is unsymmetrical, it is not stable in nature. Alright, you can see like a stone, suppose it is unsymmetrical, so it definitely is trying to roll down. But if it is symmetrical from all sides, symmetrical object like your cube is symmetrical, cuboidal is symmetrical. Alright, so they are symmetrical object, we can say. So many we are having it. So in this way, what you find is that symmetry due to what you can say symmetry, this is more stable and this is less stable in nature. Now, as it is symmetrical, more stable, so hence basically it is you will find it has got a high melting point, because symmetrical means molecules will be closely packed, tightly packed, and unsymmetrical means molecules will not be closely or tightly packed, it will be loosely packed. So as you see, it is symmetrical, it is more stable, the molecules are closely packed, tightly packed, so more energy is required to break the bond, so it has got a high melting point. Alright, it has got a high melting point and this has got a low melting point. And as it is unsymmetrical in nature, for that purpose it has got a high boiling point and it has got a less boiling point. Now, why did I use here that is melting point? Because when I said symmetrical and it is stable, so generally these are the properties of solid, and solid always melts, they never boil, understood? After melting only they boil. So hence I said it has got a high melting point, it has got a low melting point. And as it is unsymmetrical in nature, this particular one, you can say that, unsymmetrical in nature, it is less stable in nature compared to trans, so it has got a high boiling point and it has got a less boiling point. And the boiling point is also more because it has got what you can say higher dipole moment it has got, and it has got a less dipole moment. You will study about the dipole moment later on, got it in bonding chapter, because bonding chapter many more things are there. For that reason I said that chemistry is interrelated. See, if you don't understand the bonding, then you will not understand organic, and if you won't understand organic, then definitely the reactions will not be understandable. So in chemistry you cannot leave any particular chapter. It is not a semester subject. Chemistry, for that reason, they are interrelated. All the chapters are interrelated. So you need to understand every chapter. You cannot skip any chapter. If you skip means you will be responsible for it later on. Got it? So hence what you find is that here, again I repeat, it has got a high boiling point because it has got a higher dipole moment and it is unsymmetrical in nature. For that purpose, dipole moment is high and it has got less dipole moment compared to what you can say trans. See, this is a comparison I am doing it. Alright, so compared to cis, it has got a less dipole moment. Why? Because as this is symmetrical in nature, so dipole moment is almost zero or negligible here. And the molecule which is unsymmetrical, so its dipole moment is always higher. Alright, the molecule which is unsymmetrical, the molecule which does not have a regular geometry, alright, then what you find is that its dipole moment is always higher. The molecule which is symmetrical, which has got a regular geometry, geometry means what? Shape, I mean to say. Understand this word, understood? These are the technical word in chemistry. So in this way what you find is that it has got a higher melting point, it has got low melting point, it has got high boiling point, it has got low boiling point. It is more stable, it is less stable in nature. It is symmetrical, it is unsymmetrical in nature. It has got higher low or less or negligible dipole moment, zero or negligible dipole moment, it has got high dipole moment. So in this way you can see that. So basically what you find is that these are the properties which I was telling to you are the physical properties. I was talking to you about the physical properties. So if you see the physical properties, they are differing. Alright, they are differing. The physical properties are differing between the two isomers. We can say that. You know it already. That in case basically in isomerism the physical properties differs. Chemical properties remains the same. But in certain cases also the chemical properties is also differing. For example, last class I said you malic acid and fumaric acid. Now malic acid it undergoes what you can say dehydration, means it can lose a molecule of water and become anhydrous. But fumaric acid never. Fumaric acid, as it is stable in nature, as it is symmetrical in nature, so it is very difficult. It is very difficult for fumaric acid to lose a molecule of water and to become anhydrous, because when any substance loses a water molecule it becomes anhydrous. Alright. So malic acid, so what is the formula of malic acid? If you see, this is the formula of malic acid, and that is COH, this is, and fumaric, what will happen? This COH will be here and H will be here, diagonally attached. That is Fumaric is trans and malic is cis. So this is your malic acid. You got malic acid. So if you are heating malic acid, let us say at 443 Kelvin you are heating it. Then what will happen? One water molecule will be released. So here see, water molecule is released here. See, HOH. See here, HOH. Water molecule is released, and what I am getting it? What is left that I will be getting it? What is being left? Anhydrous, that is C double bond O. Here also C double bond O, C, CO, CO, and one more oxygen is here. So one more oxygen is being shared by both the carbon atoms, because carbon has got how many? There is nothing but, sorry, here this bond will not be there, single bond. It will be there. Here 1, 2, 3, 4. Here also 1, 2, 3, 4. We can say that. So here one more where the carbon goes. Oh, one more carbon I missed here. Got it. Wait. Let me write it once again. HC double bond CH, then CO, then CO, then O. Yeah, this is correct. So this is malic anhydride. This is known as malic anhydride. Clear? So in this way you will be getting it. That is malic acid, it undergoes dehydration, but fumaric does not. So this is also the difference between cis and trans, I can say that. Clear? So understood the difference between cis and trans about geometrical isomerism. Now next we will start, the next one is optical isomerism. Optical isomerism, that is, I said you the stereo isomerism is two types, geometrical and optical. So geometrical I have done, and optical I am going to start. Optical isomerism. Now first you have to understand the meaning of the term optical activity. Now there are certain compounds which rotates the plane of polarized light either towards the right or towards the left. Alright, listen carefully, you may write it down also. There are certain compounds which rotates the plane of polarized light. What I said? Plane of polarized light. Plane of polarized light either towards the right or towards the left. Either this side or this side. We can say that. It rotates the plane of polarized light. There are certain compounds. Remember that compound should be in the solution state. Then those compounds are known as optically active compounds. They are said to be S. And the phenomena is known as optical activity. Those compounds are known as optically active compounds which rotates the plane of polarized light either towards right or towards the left. Now you may ask me, sir, which does not rotate the plane of polarized light? They are known as optically inactive compounds. They are called as optically inactive compounds which does not rotate the plane of polarized light either towards the right or towards the left. They are called as optically inactive compounds. Alright, again I repeat, there are certain compounds which rotates the plane of polarized light either towards the right, or towards left. Plane of polarized light, it rotates. They are known as optically active compounds, and the phenomena is known as optical activity. We can say that. Alright, and the isomerism is called as optical isomerism. That is known as, or you can say that the compound are known as optical isomers and the phenomena is known as optical isomerism. Alright, clear now? Now we have to understand this term. What is plane of polarized light? Got it now? That when you pass the plane of polarized light through an optically active compound, suppose you will take a beaker and you will take a compound in the solution state and you pass the plane of polarized light, you will see the plane of polarized light either rotates towards right or towards the left. How you will see it? You will be seeing it by the help of an eyepiece. Eyepiece means what? Microscope. You will be seeing it. How? That is only I am going to say you now. That is only why I am going to say you now, that how you need to do it to find it out, whether the compound is optically active or not. Alright, now listen carefully. The experimental part I am going to say you. So first what you want is that first I need to prepare a plane of polarized light. Then I will pass the plane of polarized light to the solution. So how you prepare a plane of polarized light? How you get a plane of polarized light? Now you know that ordinary light means what? Sunlight. Sunlight or white light is known as ordinary light, which vibrates in all possible directions. As you can see it in here in the figure. I have drawn it in the figure. You can see that it's vibrating in all possible directions. You can draw more number of rays also. You can draw infinite, but it's not possible to draw infinite here. So this is your ordinary light or white light. It is vibrating in all possible directions. Now I am passing this ordinary light through a small slit, a small opening, that is a pinhole. We can say that. Clear? I am passing the ordinary light through a small slit. Slit means a pinhole, a very small opening. Now what will I do is that I will pass it after passing through a small slit, I will pass this light into a prism, a specially built prism which is known as Nicol prism. Nicol. What I said? Nicol prism. Alright. Now, what is a Nicol prism? Understand it. Now, Nicol prism actually, what we do is that we take two prisms, alright, made of calcium carbonate. Alright. Actually, let me go back a little bit to the history about it. There is, you have read in geography, a region called karst topography. Karst topography. ICC student, they have read in geography. CBSE, I don't know whether they have studied or not. So, karst topography, where it is found in the Iceland area, Iceland region. There you are having some limestone caves. Alright. So, when the water percolates through this limestone caves, alright. Now, Iceland means definitely will be very, very cold. Definitely. So when the water will percolate through these particular caves, now these are limestone caves, what you will find is that the water is going to freeze and it is going to form pillars which are called as stalactites and stalagmites. Some pillars will be hanging from the roof and some pillars will be from the below. Alright, so they are called as stalactites and stalagmites. So they are composed of what? These pillars are made up of. Out of that, some of the pillars, you can say, not all the pillars. Some of the pillars are made up of what you can say calcium carbonate. How? Because these are limestone caves. Now when the water percolates into it, limestone dissolves in water. Alright, and when this water freezes to form this nothing but pillars. These pillars are nothing but what? Ice. Pillars are made up of ice, we can say, which we call it as stalactites and stalagmites. Alright, so this particular pillars you will be taking it and you will cut it in the form of what you can say prism. This is a prism. These two are the prism. You will cut it in the form of prism. Understood now? When the water is going to percolate through these caves, limestone caves, alright, the limestone will dissolve in it and it will freeze in the form of pillars, in the form of ice. Got it? You will take these particular pillars which are called as stalactites and stalagmites. In geography you have studied. You will take this, what you can say, you will cut these pillars in the form of prism. Got it? These two are the prisms I have taken it. Got it? And you join it with a cementing material. Cementing means like you are joining two substances by the help of what? Fevicol or something like that you are using. So that is called a cementing material. So the cementing material is also transparent, which is called as Canda balsam. Canda balsam, it is said to be a cementing material. You will join it and you will get a rectangular glass block, this sort of. You know, rectangular glass block also acts as a prism. You have studied in physics. So in this way, what I said, you will take two what you can say prisms and you will join this particular prism by a cementing material called Canda balsam. You will join it and you will be getting a rectangular glass block which also acts as a prism, and this particular prism is called as a Nicol prism. Nicol prism. So when the light will pass out, alright, the light when it will pass out from the Nicol prism, the light is going to vibrate not in all plane, as you can see it here in ordinary light. It is going to vibrate in one particular plane. Yeah, this you can see it is vibrating in one particular plane. The light is going to vibrate, and this particular light is known as what? Plane of polarized light. Plane of polarized light. In this way we get a plane of polarized light. So hence this particular Nicol prism is called as what? Polarizer, because it converts ordinary light to a plane of polarized light. It is known as, what you can say, for that purpose Nicol prism is called as polarizer, and we are getting a plane of polarized light. Now the question might be coming into your mind, where the other light has gone. Now very simple, I will come back to physics. You now know that in physics, when the light strikes at an angle greater than that of critical angle, when the incident ray is greater than that of the critical angle, then the light, instead of suffering refraction, it undergoes total internal reflection. You have studied this in physics, that when the incident angle of incidence is greater than that of the critical angle, instead of suffering refraction, the light undergoes total internal reflection. So total internal reflection takes place. Yeah. Only except one plane of light, except one plane, where the angle of incidence is not greater than the critical angle, it is less than the critical angle, due to which it suffers refraction, and that plane is called as a plane of polarized light. Understood now? Where the other rays has got, where the other plane of light has got, it has been absorbed by this Nicol prism. How? by total internal reflection. It has been absorbed. Only one particular plane whose angle of incidence is less than the critical angle, it does not suffer total internal reflection. It comes out of the prism in the form of refraction. That particular plane is called as a plane of polarized light. Clear? So in this way we get the plane of polarized light. Thank you very much.